Hello, and welcome to another session on data mining. We've been talking about dimensionality reduction. Specifically, we've talked about principal component analysis, which is essentially a method that finds a projection vector that maximizes direction of that is along the direction of maximum variance of the data. However, what we are going to talk about today is a set of concepts that are very important when discussing data in general and that dimensionality reduction in particular. If you think about data that is given to us in terms of machine learning for different machine learning applications, those are essentially descriptors of an object. So if you want to classify good pizza from bad, you may be given a set of descriptors like toppings, what type of topping is being used, what is the dough made of, and so on, right? However, if you think a bit more on that, the different characteristics of an object can be very interrelated, right? Just like the height and the weight of a person are very much related to each other. Typically, the taller a person is, the heavier they are, right? And that justifies more exercise and stuff. And also, it can there are other characteristics as well. If, for example, if you want to measure stride length of a person, that is going to be related to their height. So at a very high level, if you think about it, different data characteristics or different attributes can be interrelated to each other, right? And we've seen this in when we were talking about these plots, these scatter plots. We can actually see that we can see different types of correlations. So if you look at this particular data that is in on your screen, you see that let's say if you got this is the height and this is the weight of a person, then you can see that there is a significant amount of covariance or there's a correlation between these two, which is the measure of statistical dependence or the measure of statistical correlation or how much change we can expect if we change one variable. How much change can we expect in the other variable, right? So that's the sort of thing that we know exists because a single point is described in an object, but we have two different attributes here, and those can be interrelated to one another. I would like you to stop the video and think of what other attributes can be interrelated for a particular person, for example. But regardless of that, what we've identified is that a number of variables can be correlated in real world datasets. And what that means, if you think about it, the probability of having a point far away from this particular high density area. By high density, I mean if you take a unit area in this, let's say if you take a square like this, and you count how many points lie in there, then you can call that as the unit density of that particular area. And you can see that this particular region that I've circled with a green ellipsoid sort of thing is an area with high density, and the probability of anything lying beyond that point is pretty small for this particular data set. So one of the observations that I would like you to make or realize is that real world data, the way we've seen, is not distributed randomly. The probability of occurring of a point is not is dependent upon other factors as well, right? So a probability of having a point here away from the cluster is it is possible to have a person whose height is this much and whose weight is this much, but the probability of that is pretty small. If you think about it a bit more, then you can realize that any data set that we have would have a structure to it. So the data that we have has a structure and that can be captured. So for example, based on the observation that we wouldn't have data going like this, for example, we wouldn't have any points in that region, we can say that the data that we have has a structure, or we can say that the data lives on a manifold. So if you want to relate what the concept of a manifold, if you don't understand what that is, the best example is us living on the face of the earth. We are distributed in different continents as humans, and there are different population densities at different areas, but we are all living on the surface of it, and probably it is not possible for us to drill through unless Elon Musk makes the boring company a bit more boring. It's not possible for us to travel through the Earth, right? So measuring distance between points through the Earth is not a particularly good idea. So if you take a step back, what I'm trying to say here is because the data has a structure, Just like because we live on the surface of the earth and we can't dig through the earth to reach from China to the US, for example. In the same way, this particular data, because it has a structure, we can exploit knowledge or knowledge of that structure, and we can try to reduce the dimensionality of that data. We've already done it. That's exactly what principal component analysis does. What it does is that we identify the direction of maximum variance, which is actually a vector along which most of the data lies, right? So we identify this particular line in principal component analysis. This is typically why most of these dimensionality reduction methods work in the first place. If there is no structure to the data, if the data is completely random, we wouldn't be able to reduce its dimensionality. And that relates very nicely to our concepts or our discussion about information theory. I want you to pause the video if you haven't seen those videos about how information theory and information content is related to variance, right? So this relates very nicely to those concepts. And and what we have over here, what PCA does is that it uncovers that structure in the data. Okay, so I hope this would give you a different perspective of thinking about your data sets, and you would now have a better understanding of what we are actually doing here in machine learning. We're trying to learn the structure of the data, and based on the structure of the data, and that is why it's called data mining as well. We're trying to understand the correlation or the interdependence between different variables. For example, how is height related to the weight of a person and so on. Then we exploit this information in multiple machine learning methods. Now, it's not always that we have such linear dependencies between different variables. Sometimes variables can be dependent upon each other in non-linear ways. What I mean by that, I'll try to explain. If you look at this particular plot, we see that height and weight have a linear relationship that captures most of their covariance. However, that may not always be the case. If you think of data points like in this plot, for example, okay, and you can think these have just been colored. These have been artificially colored. Some of these points have been colored red, the one that lie at the outside, but this is sort of a Swiss roll, okay, data set. And if you look at it, it has a structure to it, but that structure is kind of curved, just like we are on the surface of the earth. These data points live on this Swiss roll, which is shown over here. Okay, and what that means is that probably principal component analysis will not be able to uncover the structure of this data, because the structure of this data is not based on linear relationships. It's based on these curving or warping of this space into a Swiss rule. And if by some means, let's say by magic, if we are able to identify that structure, then what we can do is we can flatten it out and we can uncover that particular structure. So think of, instead of, just like we're trying to project our data onto a straight line over here, right? And then if we transform it, we can see that the major axis is now going to be aligned with the x-axis and the minor axis is going to be along the y-axis. If you start thinking of the same thing like that, but instead of a straight arrow, if you think of it like we're trying to project our data onto a curve, like this one, the one I'm drawing with green. And then what I do is I try to flatten it out. This is what I'm going to get, right? So this is what is called nonlinear dimensionality reduction. So dimensionality reduction techniques can be based on the linear understanding or the linear relationship between different variables, such as principal component analysis. And some methods can also be based on nonlinear or on identifying nonlinear relationships between different variables, just like this one. The relationship here is being modeled by this particular Swiss rule that is over here. And if you want to read more about this particular method, you can read about it here. But there's a bigger picture here. There's a more generic concept. Data lies in manifold. Data has a structure. That structure can be linear, in which can be captured using correlations, or this can be captured using variance. And it's important to understand how these relate to information theory measures or information theoretic measures. So how does this relate to entropy? But there can be non-linear dependencies as well, and those can be captured using other methods. So one way to capture those can be if we, for example, instead of trying to measure correlations, if you want to capture mutual information between two different variables. And I welcome you to explore that on your own a bit. But there are a number of dimensionality reduction, nonlinear dimensionality reduction methods. One of the first ones, or one of the real early ones, was this locally linear embedding method, which was published in Science in the year 2000. But there are so many others. The important thing that we are trying to understand here is the relationship between information, how two variables are correlated to each other. So knowing one variable, what does that inform me about the other one? That is the essence of dimensionality reduction. If we are able to understand that structure, then we can then we can go ahead and reduce the dimensionality, and then we can try to use the reduced dimensionality concept for visualization. We can use it for machine learning and other purposes as well. Okay, so I hope this helps to understand why we are able to do dimensionality reduction. Moving on, there are different variants of principal component analysis. There is incremental principal component analysis. If you are running low on memory, this is something that you may be interested in. What it does is that instead of calculating the covariance matrix of all of the data, you can do a batched version of it to identify those maximum variance directions. Okay, so it's available in sklearn. I welcome you to explore it on your own. One of the problems with principal component analysis is, like, if you've got data like this, right, and you're very happy, you can have a maximum direction of maximum variance like this one. But if we have an outlier, a data point that lies far away from where the rest of the data is, then principal component analysis is quite sensitive to that. And what I mean by that is that instead of giving us this particular feature vector, projection vector, it's gonna this the occurrence of a single outlier over here is gonna change this direction, and it's going to have an impact on that. So you may not be able to uncover the true structure of the data if there are outliers over here. And if you're not familiar with the concept of outliers, I'll be happy to explain. So let's say if you're trying to measure temperature, and you record your daily temperature, and you get a certain value. You can identify what season it is based on looking at temperature data from historical in a historical perspective. But what if someone messes with your thermometer? What if someone puts it into a cup of coffee? That's gonna, well, first of all, why would someone do that? That's another problem. But that malicious act can lead to an outlier. So an outlier is something that is atypical, right? So in such cases, principal component analysis, the projection vectors that we're going to get can be skewed away from the true structure of the data. So don't want that. Fortunately, someone came up with an algorithm that is called robust PCA, which actually disregards such malicious intents or outliers, and they are able to recover the true structure of the data. Okay, so this is also available in Python. So if you want to go ahead and try it out, feel free to do so. Now, if you look at principal component analysis, you would realize that essentially it is a projection method, right? We've got W transpose X, and then that is what we get. What that means is that we can write this W vector in terms of the data points that we are given, right? So this is the representative theorem, okay? And what that allows us to do then, sorry for the horrible writing, but you get the idea. We have the representative theorem here. We can write the vector in terms of the given data points. And what that allows us to do is to express this projection in terms of this. So if I substitute this thing into there, what we are going to get is we're going to get this. I is equal to 1 to n alpha I xi transpose into x. Okay. And this is a dot product, and we can replace it with a kernel, right? This is called the kernel trick. And that means we can kernelize principal component analysis, and that would allow us to do nonlinear dimensionality reduction using principal component analysis, but together with the kernel. Okay, so the same concept that we studied in support vector machines It's applicable over here. We can kernelize principal component analysis, and kernelized principal component analysis can do nonlinear dimensionality reduction. So you're welcome to explore that on your own if you ever need to. Okay, need to use it. Okay. So those are some of the variants. There are other dimensionality reduction methods. One of them as well. One of them is called linear discriminant analysis. Now this is different. Principal PCA is principal component analysis, whereas this is discriminant analysis, and that's a major difference. So PCA is unsupervised. It doesn't use any class labels, right? The only thing it used was a data matrix in which you have n examples, each of them in d dimensions. Whereas this method called linear discriminant analysis is a discriminator method, and it works by using both this data matrix, which is X, together with the labels. So let's say if you got class labels can be positive and negative, right? So linear discriminant analysis gives you a projection vector, just like principal component analysis. So if you talk about principal component analysis, you've got these data points, and then you get essentially a W vector, and you project your data onto that, and that allows you to reduce dimensionality, right? So essentially, if you think about PCA, if you think of it as a black box, data goes in, and out comes a set of projection vectors, right? In the same way, LDA is a bit more than that. What it does is that it takes in X, which is the data matrix, and it also takes in the labels of those examples. So it's a supervised dimensionality reduction method. And it can also be used for classification, by the way. And out comes a set of projection vectors again. So the output of both of these are the same, but the way this projection happens is a bit different. The way LDA works is that it finds the direction. So let's say if you got two classes, if you got two, if your data contains two groups or two classes, one of them is X's and the other one is O's. We're going to call the mean of all the points in the X class as M1, and we're going to call the mean of all the points that are circles M2. So we have two classes, 1 and 2, let's say, and we have a certain spread of this class, this X class, which is this much, right? Oh, sorry, which is this much along the x-axis and y-axis, and this much along the x-axis. Similarly, we've got these two as the variances along the x and y direction for the O class. So this is the X class and this is the O class, and we have got this respective variance. And the way linear discriminant analysis works is very simple. It finds a direction so that if you project all of your data of the two classes onto that vector, the the points of the two classes are as far away from each other as possible. Okay, and the points of the same class are as close together as possible. So it increases the distance between classes, but essentially tries to reduce the distance within the class. So let's say it's really easy to think of it intuitively rather than in terms of mathematics. Let's say if I project all of my data onto this green vector that I just drew, then I can project all of these points there, right? And we can say that the distance between these two classes is, let's say, this much, right? And the spread of each of these class for X class is this much, and then the O class is this much, right? Now, what we are interested in finding is a vector or a direction vector that maximizes this distance, which is called the betweenness distance, okay? So we want to find a direction vector so that if I project my data, this distance between the classes is maximized. More specifically, the distance between the means of the two classes after projection is maximized. Similarly, we want to find the vector that also reduces the spread after projection of each of the classes. So the clusters are as tightly packed as possible after projection, okay, for each of the class. And if you think on that criteria, then the direction you're going to get is probably this one, okay, which is roughly the same direction as principal component analysis, right? In this case, in this particular case. And if you project your data along this direction, then the distance between the means of the two classes, sorry for the horrible overwriting that I'm doing over here, but I hope you're getting the point. So the distance between the means of the two classes are now going to be as large as possible, and the variance within each class, or the points of each class within each class, is going to be as small as possible. So that is what linear discriminant analysis does. It's a supervised method for dimensionality reduction. It finds a direction such that the distance between the means of the two classes, in this case, is maximized, while maximizing the dispersion of data, while minimizing, so this should be minimizing. This is a typo. Sorry about that. While minimizing the dispersion of data points of each class around its mean. Okay, so that's what we want to achieve. If you want to read more on that, you can go through this book. We're not gonna cover the mathematical basis of it, but in the end, this also comes down to an eigenvalue problem. So it shouldn't be too hard if you already know what principal component analysis is all about, and you're welcome to use it in solving different types of machine learning problems. It's always available. It's also available in sklearn. Let's say if you want to see how this can be useful for your assignment, please go ahead and try it out. Okay. There are other methods of dimensionality reduction as well. One of them is called multidimensional scaling, and that's pretty popular. So let's say if you got a data matrix in which you have n points and each of them is in d dimensions. So what we want to do in multidimensional scaling is that we want to project. So if you apply MDS on this particular data matrix, what we want to do is we're going to reduce the number of dimensions, right? So we get another matrix that I'm going to call X prime, and we have got the same number of points as we had originally, but the dimensionality has been reduced. Let's say we had 10-dimensional data in the original feature space, and we want to reduce it to say 2-dimensional data. Now that's what PCA does as well, right? That's what all of these dimensionality reduction methods do. But what's special about MDS is that it ensures that if 2 points that were far away in the original feature space, they would still be far away in the reduced feature space. So it preserves this distance between these points. So if 2 points were close together before the dimensionality reduction, before MDS, they're going to be together after dimensionality reduction. Okay, so that's the basic idea of multidimensional scaling. It reduces the number of dimensions in the data while preserving pairwise distances between points. Okay, so let's say we live in a three-dimensional world, right? So if you take the altitude and the height and the width of each of these cities, European cities, and then you reduce the dimensionality and project it onto 2 dimensions. This is the map that you're going to get for different cities in Europe. So as you can see, it's not ideal. Like London and Dublin, they are close, and London is closer to Paris, so that's preserved, and Paris is close to Zurich. But it does lose some information because Paris and Madrid, it should be in the map. I think it's probably over here, but that's the sort of effect you get in terms of multidimensional scaling. So it's a very useful method when you want to preserve distances. Another good thing about multidimensional scaling is since it tries to preserve distances, all you need is distances between points in order to do dimensionality reduction. So this particular MDS was essentially done by giving it a matrix of distances between all pairs of points. So let's say we've got how many cities we've got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 cities. So what we do first, the first step is we calculate a distance matrix, which is going to be of size 12 by 12. You can use Euclidean distance. You can use whatever distance you want. And once you get this distance matrix, what can happen then is you can for each of these 12 cities, you can get a two-dimensional representation, which this is, that preserves these distances in this particular space. So it's only based upon this distance matrix. So that's one of the good things about this multidimensional scaling method. So you don't need features even. All you need is pairwise distances. Let's say if you want to calculate the distances between strings, for example, all you need to measure is how similar those strings are. Let's say if you've got a program that takes in two strings and spits out a number of how dissimilar or similar those strings are, you can use MDS to represent that particular data point, that particular data set of strings into a plot, okay, just like this one. So that's one of the good things, okay. There are other methods as well. There's a very popular method these days, which is called T-distributed stochastic neighbor embedding. Okay, and that's a mouthful, but and we're not going to cover it in detail in this particular module, but it's one of the very effective methods, one of the very effective methods for dimensionality reduction of very high dimensional data. So what it does is that it reduces dimensionality, of course, while preserving the local probability distribution of the data. And what that means is that it tries to preserve local data densities, and that's where it gets its name of T-distributed stochastic neighbor embedding, because it tries to embed neighbors using this particular property of trying to preserve local probability distribution within the data. And you're welcome to try and look online for different types of plots for TSNE. What I'm going to talk about next is another method called UMAP, and it's another method that can do an amazing job in reducing dimensionality as well as generating visualization. So in your assignments, you've been given a high dimensional data set, right? It probably around 1,000 dimensions or higher even, I don't know. But if you want to reduce those dimensions into and you want to visualize that, say, in 2 dimensions, one of the things you can try together with principal component analysis or MDS is UMAP, and I'm just going to demonstrate what it does in using a web link. Okay. Okay. So UMAP stands for Uniform Manifold Approximation and Projection. It's essentially a local projection method. So it identifies local directions where you can project your data and then visualize it. Okay, and it has got really this really nice library in Python that I welcome you to try out on your own, and you should be able to. You'll be impressed with the types of demos that they have. It's called the UMAP Zoo. You can look at different types of visualization. What I'm going to show you is a visualization of MNIST, of the MNIST dataset. Okay, so this is the MNIST. This is a projection using the MNIST dataset using UMAP. So I am not sure why I'm not able to see it. Okay, so this is the visualization of MNIST using UMAP. So just like we generated the visualization for MNIST using PCA, this is just a change of the method from MNIST to UMAP. And what it shows you is different digits are colored in different ways, and we can click on, this is an interactive demo provided by the UMAP library, and I'll be posting the link so you can explore it yourself. What it allows you to do is you can click on a particular digit, and you can see what that particular digit looks like, right, in the top left corner of your screen. And you can, so what goes into this is in this analysis is each image, which is I think a 28 by 28 image. So that's 784 dimensional that goes into the UMAP, and out comes this plot that you can then color with respect to the labels of each of the digits. So I think ones are whites, yep, and in red we have threes, purple we have 8. But what this allows us to do now is we can zoom in and we can see where do confusions occur. So for example, this one in its feature representation is quite close to a 2. And I'm beginning to see why, right? You can zoom in and you can identify, you can use this data mining approach, this simple projection approach uh, to understand if there's going to be mislabeling, for example, or if there are any outliers in your data. So for example, this 3 uh, which is a true 3, so that's indicated by the red color, is closer to 8s, and that makes sense, right? It's almost an 8. So we can use this for such analysis. Similarly, we can do we can do a more detailed analysis of what classes are closer to each other. So in this particular analysis, we can see that this purple bit is eights, and then we've got these fives, which are essentially close to each other, and then these fives are closer to threes, and then there is some mixing going on in there, as you can click on one of those, and you'll be able to see that. So it's a pretty powerful method, and it has a very simple library that you can use for your own analysis, and I welcome you to explore it. One of the things that I must warn you about is that please try to read the documentation and read the method and try to understand that before you start using it. There are two different variants of UMAP. One of them is supervised and the other one is unsupervised. And depending upon what your particular needs are, you may want to use one or the other. Okay, but please go through. It has a certain set of hyperparameters as well. The principal component analysis method has only like one hyperparameter. You can control how many dimensions you want to project into, and that controls how much variance is lost, right? In these methods, in these UMAP, because they are non-linear dimensionality reduction techniques, there are a bunch of other parameters. There is a neighborhood constraint, and there are a few others that have an effect on how these plots are generated. So it's important to understand the role of those parameters before using that. Okay, so please go ahead and read through the documentation before you plan to play with it. Okay, but in general, I hope you have found the use of these dimensionality reduction methods. You would have enjoyed it, and you would try to go through the tutorials and the exercises and use them in your machine learning and data mining projects. Thank you.